Hello all, welcome to my presentation. Hello all, welcome to our presentation on cavitation bubble dynamics in a Rankine vortex. I'm Pranav Mohan and I'm accompanied by Dr. Sadiq Dabiri from Purdue University. So I wanted to provide a brief flow visualization before we actually proceed. So we have a vortex basically in the z-axis, and we observe that initial bubble actually grows axially, and this is what we are trying to study. So, so cavitation can actually hinder various applications in various forms, such as noise, vibration, and erosion, and it can lead to a reduced performance as well. And that is why we need to study cavitation better, so we can mitigate or take or erase those effects. Now, tip vertical cavitation is a canonical problem that may give insights into other problems as well, which is what we are studying. And cavitating vortices can be found in various applications, such as turbomachinery and blade surfaces as well. The pressure at the core of the vortex, if the circulation velocity of the vortex is very high, the pressure at the core can drop even below zero. And when that happens, it can lead to basically very, very low stagnation pressures at the core. And if there are any nucleation sites present at the core of the vortex or anywhere in the region of the vortex, it can lead to cavitation, which is what we are trying to study. Now, cavitation bubble dynamics in terms of growth, splitting, and collapse is not very well understood. And finally, the vortex is actually inherent to all turbulent flows, and we believe that vortex cavitation may give us further insights into understanding turbulent flows better. So we want to isolate our study on a single bubble vertical cavitation. So what people have done in literature is Choi et al. In 2009 used axisymmetric conditions to predict a cylindrical shape during the growth of the bubble. And they basically modeled the growth and the collapse of the bubble separately. And the output of one model led to the input of the other model. Now, dynamics inside the bubble has also not been very well explored, and this may be due to the inertia effects of the bubble being really small, because the density of the bubble is much smaller in comparison to the liquid around it. Through our simulations, we have also observed that there are some re-entrant jets that are formed, which has also not been explored. And also there is not any experimental work in this region also available. However, there is experimental work on modeling this cylindrical growth. So Choi et al. In 2007 basically observed through experiments that the bubble actually does grow axially, as you can see over here. And there are various other effects that come into factor as well, such as the water quality effects that we have not taken into consideration in our study. So we are doing direct numerical simulation using an all-max solver on Basilisk. If you want to model multi-phase flows, Basilisk is actually a really useful software for that. If you have any questions, let me know. So using the all-max solver, we are solving a conservation of mass equation. We are also solving conservation of linear momentum. And here's the equation. And we have the viscous stress tensor. And we also take into account the surface tension effect, since we are doing a multi-phase simulation. We also solve the energy equation with the absence of thermal diffusion and any mass transfer effects. So those are not taken into consideration here. And finally, to close the system, we have the equation of state, which relates pressure to density as well. An important point to note here is that the B for water is actually 3049.13, and people in literature have used various values. However, we have stuck to this value after validating this and making sure, and this value works best for us. So we have a cubic Cartesian grid, as can be seen in this figure, where we have a bubble at the center and the coordinate axes have been defined. So the Rankine vortex, and we specify the initial conditions in this cubic domain. So this is a rank. So at the initial condition, we specify the Rankine vortex, where the velocity is given as this and the pressure is given as this. The pressure can actually be derived by plugging in the velocity in the Navier-Stokes equations. And we also have the equation of state, but here I have rearranged the equation in terms of density, and the constants are same as before. So various simulation parameters have been defined here. So first we have the cavitation number. So you can think of cavitation number as a parameter for how strong the vortex is. It is given by the pressure, the radius of the vortex, the density, and the circulation of the vortex square, using those four variables. And the stronger the circulation velocity is, the lower the value of sigma will be. So the stronger your vortex, the lower the sigma is going to be. We also have the bubble to vortex size ratio, which gives radius of the bubble over the radius of the vortex. And this can basically represent how small or how big the nucleation site that we are going to induce in the computational domain with respect to the radius of the vortex would be. We also have the aspect ratio, which is given by R, which we can define as a radius for the bubble along the radial direction. And we also have L, which is the half axial length along the Z axis, where the bubble grows cylindrically. And we can order and we can define aspect ratio like that. And as previously mentioned, we also take into account the surface tension effects. And however, for our simulations, for these particular sets of data, we plan to keep our surface tension fixed at 72 millinewtons per minute, per meter, sorry. So to provide a brief flow visualization, this is the same GIF that was playing before. Due to the very negative pressures at the center, a very small cavitation, a very small gas bubble can actually grow like this, as shown in the flow here. And there are various behaviors that can be described here, such as growth, and then there's pinching, and then it leads to elongation, and finally fragmentation at the end. However, due to time constraints, we will only be considering the growth part in this presentation. So before we even put in the bubble in our simulation domain, we want to first look at a vortex and see if it diffuses well over time. So we have a counterclockwise rotating Rankine vortex in the domain with the radius of 10 mm. And we observe that over 10 milliseconds, the velocity, the maximum velocity, which is actually at the radius of the vortex, basically decreases by 20%, and the pressure at the core actually increases slightly also over the time that we are considering. Finally, since this is the 3D domain, we also have plotted the pressure at the x-axis, and we observe that everywhere on the sides, the pressure remains constant, whereas in the core of the vortex, or the center of the vortex, the pressure slightly increases, as can be seen on this plot as well. Finally, now we look at the actual results with the cavitation number. So we look at the effects of cavitation number, and over here we have a semi-log plot. On the y-axis, we plot the volume of the bubble, non-dimensionalized, using the initial volume of the bubble for various cavitation numbers, and we observe that from an initial non-dimensional volume of 1, the bubble can grow up to 4 orders of magnitude higher. And then the bubble volume actually increases, and then it decreases, and then it increases again. So there is basically a cycle. There's an oscillation, and obviously, if this was if the vortex was not there, there would be an oscillation of the bubble volume, where it increases and then decreases and then increases again, described beautifully by the Rayleigh-Placid equation. However, because we have the vortex, we still observe the oscillation. However, the oscillation period is different for various cavitation numbers, as well as the difference in orders of magnitude between different cavitation numbers is also of the order of 2. And this growth that we are observing, this volumetric growth that we are observing, as was shown before in the video, is more in the axial direction than in the radial direction. And in the radial direction, there are actually oscillations, but in the axial direction, there are the bubble grows, and this is further defined using the aspect ratio of the bubble. So over here, aspect ratio of the bubble is being plotted over time at different cavitation numbers, and aspect ratio again is defined over here. And we observe that for the lowest cavitation number, which is the case for when the vortex is the strongest, we get the least aspect ratio. So that means the growth that we are getting along the axial direction is the maximum, and that makes sense when the circulation velocity is the highest and the vortex is stronger. However, for all the cases that we considered, the aspect ratio is still less than 1, and the bubble grows cylindrically along the axial direction as well. We also look at the effects of the bubble nucleation sites. So here we have bubbles of different sizes in the same computational domain at this particular cavitation number. And we observe that even though the bubble actually starts at different initial conditions, they all lead to the same result in terms of the volume. So here, the difference between the previous volume plot I had, volume versus time plot I had, was now the volume is actually not in a log plot. And we observe that we get the same volumetric growth independent of the initial conditions that we choose. We also observe that the aspect ratio is also same for the three cases that we looked at. So to conclude, various variable density Navier-Stokes equations are solved to simulate cavitating vortex. And the growth, we found that the growth of the bubble is strongly dependent on the cavitation number and the vortex core pressure, which is what is described by the cavitation number. The growth is much, much larger in the axial direction than the radial direction, which was specified by the aspect ratio plot. And finally, the size of the nucleation site does not affect the bubble dynamics at all, as the volumetric growth for various sizes of bubble was the same. So thank you. Please leave your questions in the chat, and thank you for interacting and watching my presentation. I appreciate it.